Okay, so today we're going to go over all the stuff that was the physics unit. Okay, so we started out this unit and we were talking about, first off, okay, whoa, that's not how you spell types. Types of energy. Okay, and in there we talked briefly about things like electrical, okay, chemical. Man, I'm having all kinds of trouble spelling this morning. Okay, chemical, we talked about magnetic, okay, thermal, okay, etc., etc. Okay, that was kind of that first day, and we talked about a few of the people who were important, like Oersted and Faraday and Joule and guys like that. Okay, I would say that guys' names are not something you should spend a great deal of time on. All right. On the unit exam, I think there's 2 multiple choice questions that involve people's names. All right, so it's not something you should go over with a it's not something you should spend a lot of time on. Okay, you're gonna spend a lot of time on something. What should it be? Graphing, work energy theorem. Those are the 2 big ones. Okay, those are the 2 you definitely need to spend your time on. All right, people's names you'll probably recognize from the context of the question if you've read your notes over a couple of times who it is. All right, they're relatively obvious. All right. After that, we talked about technology and thermodynamics. Okay, and on this test, some of the multiple choice deals with this topic, but it's not strictly recall. All right, you will have to apply and synthesize a little bit, okay, with these ones. So a little bit of higher level thinking skills to do with especially thermodynamics. All right. When we started talking about thermodynamics, the first thing we talked about were the types of systems involved. Okay, and there were 3 kinds. Anyone remember what they were? Isolated, open, closed, and isolated. All right, and the differences between open, closed, and isolated were whether they could exchange matter or energy or both or neither, okay, with their surroundings. All right, and the surroundings are anything that is around the system. All right, so an open system, okay, is exactly as the name would imply. Okay, matter and energy. Closed system. Energy. Okay, energy only. And isolated? Theoretically, neither. That's not how you spell neither. Neither is that. It never looks right. Neither never looks right whenever I spell it. I before E except after C except most of the time. Isn't that how the rule works? It is EI because, of course, it doesn't follow the I before E except after C rule. That's why I teach physics. Okay. All right. So those are the systems, and then we talked about the laws of thermodynamics, and we talked about those several times throughout. Okay, throughout this unit here. So laws of thermodynamics because they have to do with transfers of energy, and that's the work energy theorem. All right, so that's why they're kind of important and how they'll sort of be introduced in the exam, as well as what kind of things you'll have to tie them into. All right, so laws of thermodynamics. First law, okay, is basically the law of, okay, conservation of energy. I'm going to abbreviate C of E. Okay, law of conservation of energy. Okay, which, I mean, energy can't be created, it can't be destroyed, but there were other implications of that. It also meant that if you wanted to increase the energy of a system, what did you have to do to it? Give it some of your energy. What do we call that? Work, right? You have to put work in. If you want to increase the energy of a system, you have to put work in. Once that work is in the system, it can be converted to any other type of energy. All right, everybody follow me there. Now, the other thing that the first law also implies is that while the amount of energy may remain the same, it doesn't mean it's doing useful work anymore. Every time you convert one form of energy to another, what happens? Do you lose some? But you don't really lose it, do you? Okay? It's still there, it's just not doing what we want. It's some form of energy that is less productive, sound, thermal energy, etc. This is a law of conservation of energy. So we're just talking, you can't create it, you can't destroy it, but these are some ways you can change it. Okay, the law of conservation of energy doesn't say you can't change it. It just says you can't create it or destroy it. If you want to put more in, you have to do work. Okay, and a system can lose energy by doing work on something else, but it doesn't mean the energy has been destroyed. It's just been turned into something else. All right, so those are kind of the things to remember about that. Okay, and then the second one has to do with direction of energy flow. From? Yeah, hot to cold, high to low. Okay, just like any natural system, we always go from a high energy to a state of lower energy. Okay, you don't make something hotter by adding cooler stuff to it. Okay, that's generally what that's saying. All right, so we talked about laws of thermodynamics, okay, and then, you know, obviously that's, I mean, we talked about those all throughout the unit. We kept coming back to them, all right? The next thing we talked about, scalars and vectors. Okay. What were the scalar quantities we dealt with? Speed is a scalar quantity. Distance. Time. Energy. Okay. Work. All right. All of those are scalar quantities. All right. The ones we have the most sort of problem solving probably to do with in terms of whether it matters if they're scalar or vector are speed and distance. All right. The thing to watch for on the unit exam is wording in the question. All right, and I'll usually boldface or italicize or somehow stand out the word I'm looking for. Okay, but if I give you a question that says so and so went, 5 meters north, then 10 meters south, and the whole trip took 30 seconds, what was their speed? Okay, does the north and south matter anymore? No, okay, but that's what you have to look for. You got to read that question carefully, because I'll do that because I'm a jerk. Okay, I'll put directions in there to get you thinking vector. Okay, and see if you remember speed's not. All right, you guys follow me there? Okay, so it's important to know the difference between your scalar and vector quantities, because how you might solve a simple multiple choice question like that, okay, would make a difference. All right, vector quantities. Displacement, what else? Velocity. Acceleration. Okay, those are the big ones for sure. All right, force is also a vector quantity, but we don't use it very much other than the work energy theorem, so the fact that it has direction doesn't really matter for us. Okay, again, just look for those words, make sure you know which ones are vector, which ones are scalar. That is something you're just going to have to memorize. All right. You will be given all the formulas, obviously, on the unit exam, not your formula sheet, because I have no idea how much stuff you've written to yourself on there. Okay, if you have hints you absolutely can't live without that you've written on your formula sheet, you best memorize them over the weekend. Okay, because you will get formulas on the front page of the exam. Did you sign in, Jordan? All right. So does that sort of make sense there? So I am going to ask some multiple choice stuff about scalars and vectors, but it'll be simple stuff. Most of the multiple choice stuff, okay, would be V equals d over t, or V equals d over t. All right. Where would I ask acceleration questions, do you suppose? In the written, yeah, okay. The written response, problem solving, 4 or 5 mark question for an acceleration problem. Okay, so make sure, okay, that you can use that one, okay, because that'll be written response for sure. Okay. Is it possible that all of these things here could also be part of our next topic? Yes. All right. Now, again, read the questions on the exam carefully, especially the written response item on graphing, because sometimes there's more than one way to get something off of a graph. All right. If it says, let's say, calculate acceleration from this velocity time graph, are there two ways to do that? Yes, final velocity minus initial velocity over time, or what? That is the slope of the best fit line of that graph. The question will tell you which way it wants you to do it. All right, so read the question carefully and do it the way the question asks. All right, because that question isn't necessarily saying, I don't care whether you know how to do this. I don't care whether there's two ways to do this. It's saying, I want to know if you can calculate the slope of a best fit line. That's why I want you to do this. Okay, everybody follow me on that? So make sure you do it the way the question asks, and it will say one way or the other. All right, if it doesn't say, then you can do it whichever way you want. All right, but if it does say, make sure you do it the way you're asked. All right. Okay, so graphing. There's only two kinds of graphs. Okay, position versus time, and velocity versus time. It is very important that you know what you can get and how from each type of graph, because there are many of each type on the exam. Some in the multiple choice, some in the written. Okay, in fact, if I recall, there's 2 graphs in the written and 4 in the multiple choice, I believe. I'll double check on that for you, but okay. There's lots of graphing. There's lots of marks on graphing, so it's something you should definitely know. All right, on a position versus time graph, what can we read directly off the graph? No, I would have to do a very small calculation to get displacement. What can I read directly off the graph? Again, have to do a small calculation to get distance. I can get both of those things, but I can't read them directly. I'll give you a hint. It's in the name. Position and time. Okay, that's what you can read directly off of that graph. I'm not trying to trick you on that one. Okay, but a question may ask something that simple. Using the graph below, where is the object at time 5 seconds? All right. Okay, or using your best fit line, where is the object at time 5 seconds? Okay, it's not hard to do, but you got to remember how to do it. All right. It may ask, what's the displacement between 6 and 10 seconds? How do we find that? Final position minus initial position. Okay, if we're trying to find the distance traveled, we got to add up all the little distances traveled in each part of the graph between the times we were asked about. Okay, how would we get velocity off of that graph? Slope of the line, if there's a best fit line. If there are multiple lines, like multiple angles, so let's say the graph looked like this. Okay. Final position minus initial position over total time. Okay, is that this formula up here? Yeah, okay. So in a case like that where you don't have a best fit line, that's what you'd have to do. You'd have to go back to the formula then. Okay. On a velocity versus time graph, we already said the slope of the line is essentially this. Okay, and we'll give you acceleration. The area underneath the line gives you displacement because it comes out to meters squared. Or sorry, it comes out to meters, not meters squared, meters. Okay. All right, so make sure you're ready for that. Okay, you've got a graphing worksheet, and the review sheet I gave you yesterday has several graphs on it as well, and they are old exam questions. All of the graphs that are on yours were on exams prior. Fourth drawer. Okay. All right. Next thing was acceleration. Okay, and we already said that's written response. Okay, problem solving. Should you show all your work for that? Yes, please do. Okay, the answer is I mean, if you get the right answer and show no work, I will still give you full marks because you're either a brilliant guesser or you knew what you were doing, and I can't tell which. Okay, but if you get clumsy-fingered on your calculator and do everything right except the answer, it's nice to get 4 out of 5 instead. Okay. All right, then after acceleration, we started talking about work energy theorem. And we talked about that for a good portion of the units. Okay, where will I ask about work energy theorem? Okay, I'll have problems in the written. But can I test your understanding of the concept in the multiple choice? Yes, okay. Work energy theorem is everywhere, all right, expected in both sections of the exam. All right, so multiple choice, okay, understanding of concept. Okay, and maybe applications. There may also be a written response item where you would have to apply your knowledge and write something. Okay, but mostly we're going to be looking at problem solving. Okay, in the written response, you have many, many solved examples in your notes, on the podcasts, okay, quizzes, all of that. If you're still having trouble with work energy theorem, I highly recommend watching all of those. Best way to find them, okay, especially if you want to do the quizzes, go into Power School, go to the work quizzes, and click on the link to the podcast that's right in there. All right, that's probably the easiest way to find them rather than watching a bunch of podcasts and seeing if they have quizzes on them. All right. Also, watch the podcast on work energy theorem. There's what, 4 or 5 of them? Okay, there's a bunch. Okay, so watch those if you're still having trouble with that. Okay, so I don't want to shortchange that. It's big, really, really big, but there's not much else to say about it. Okay. From there, we went to conservation of energy. Okay, that's EI equals EF. Expect a problem on the written response on conservation of energy. How do I tell the difference between a work energy theorem question and a conservation of energy question? Right, okay. Now, the thing to watch for when you're looking for things that might be a distance, might be a height, both work energy theorem and law of conservation will give you height sometimes. Okay, a work energy theorem question could give you a change in height if it's changing what kind of energy? Potential. All right, so the thing to watch for really is force. Okay, look for the word work, look for the word force, look for newtons in the question. If those are in there, it's work energy theorem. All right, if it's a roller coaster or a person tobogganing down a hill or any of those kind of examples we went over, it's law of conservation of energy, okay? Especially if there's no work involved in the question. All right. And then, last thing we talked about was this efficiency. Okay, and I told you there's not going to be much in the way of problem solving on that. 2 multiple choice at the most. Okay, the formula's on the formula sheet, and I'm sure that you'll be able to use that effectively. All right. Now, it doesn't look like much, but we spent a lot of time on 2 things, graphing and work energy theorem. Okay, so those are the big ones. Okay, obviously being able to do problem solving of any kind, v equals d over t, acceleration, all of that is really important. There's lots of marks there on those concepts. Okay, and then for the multiple choice, it's reading over your notes and being able to demonstrate your understanding. Okay, a little bit more detail here about your exam. Okay, so there are 20 multiple choice questions. The written response, there are 7 for 46 marks. Okay, some of them have an A, B, and a C. That's why I'm not saying that each one is out of 6 marks or something like that, but there's some that have an A, B, and a C part, so that's why it's out of 46. Okay, so the whole test is out of 66. Like I say, your formula sheet, I basically just copied and pasted onto the exam, so everything that's on your formula sheet is on the test. Okay. So multiple choice, like I said, there's some stuff on work, energy theorem, there's some stuff on types of energy, thermodynamics, systems, heat pumps and heat engines, okay, and has to do with the second law of thermodynamics, vectors and scalars, graphs, acceleration, types of energy, work energy theorem, energy, work energy theorem, efficiency. So, gives you a pretty good idea the distribution there. Okay. In the written response, graphing. First question, graphing. Okay. An acceleration problem. More graphing. Work energy theorem, conservation of energy, and an acceleration problem at the end as well that will make you think. No, it's not about Star Trek. Okay, that's it. That's what's on there. All right, so you got a pretty good idea now, I think, of what things you need to go over extensively and what things you only need to go over, let's say, a very small amount. All right? Everybody with me there? How many people got started on the review questions yesterday? Okay. Any questions on the review questions? All right, well, you've got about another 20 minutes or so to work on that, okay, or whatever form of studying preparation you want to do for this exam. As long as you're using the time effectively, you have it. All right, if you have questions, please ask, and we'll go over them. Okay, so the mistake is right here, guys, on number 9. This should end up being 2.39 or 2.4. Let's say it's 2.4, not 8.4. I'm not sure what happened there, but okay, there is a mistake on there. It should be 2.4 kilograms. Okay, as 200 over 9.81 times 8.5 is not 8.4. Okay. Okay, so number 11 here on the review, guys, it's a good one because it's one of those two-part V equals D over T questions. All right, so what we want to do is write down our givens for each part. So in part 1, we know that it averages a velocity of 12 meters per second south, which is important, okay, that it's south. Okay, and it does that while covering 6,500 meters. So that would be a displacement because we know it is also south. Right, what we don't have is the time. And then in part 2, okay, we know that it travels 3,400 meters north. And it takes 8.5 minutes to do that. We should probably convert that to seconds by multiplying by 60. Okay, so let me do that. Okay, so 8.5 times 60 is 510 seconds. Okay, we should probably also find the time for part 1 because we can't find average velocity unless we have total displacement and total time. All right, so time here, time is going to be d over v, 6,500 over 12. All right, so we've got 541.7 seconds. All right, how do I get the total displacement here? If I go 6,500 meters south and then 3,400 north, I subtract them. Yeah, they're opposites, right? I can just subtract. I can't do final position minus initial position because I don't really know what those are. Okay, but I can go 6,500 minus 3,400, okay, over the total time, 510 plus 541.7. Okay, and that will give me my average velocity over the whole trip. So, in brackets on the top, 6,500 minus 3,400 divided by 510 plus 541.7 gives us 2.9 meters per second south. Okay, how do I know it's south? Well, I subtracted them and the south number was bigger. Okay. All right, does that make sense? Okay, any others? All right, don't be afraid to ask if they come up. Okay, so number 12 is one of those questions that you have to read very carefully. It doesn't seem like on the surface it gives you very much information, but in fact, it speaks volumes. All right, so a hammer falls off of a rooftop. If it falls, how fast was it going? Okay, so its initial speed is 0 meters per second. As it falls, what's going to happen to its speed? It's going to gain speed, right? Because it's doing what? Accelerating. All right, that might be an important thing to know. This is an acceleration question. All right, so we don't know what VF is. That's what the question asked for. So if I have VI and VF, this formula right here is out. Because that formula only works when something travels at a constant speed. A falling object does not. Okay, what rate does a falling object accelerate at? Do you know the time for this question? Do you have a formula that contains VF, VI, A, and T? Okay. All right. Solve them for VF. Doesn't seem like that question gives you that much at the beginning. Okay, but again, you got to read it carefully. If something falls, if it's dropped, the initial velocity is 0. All right, it's asking how fast is it going when it hits the ground. That implies there's two different speeds. Agreed? Okay, not a constant speed. It implies there are two different speeds. All right, so that means it's an acceleration question. And okay, most acceleration questions that involve a falling object will not outright give you 9.81. You have to remember it. Or you have to, well, I mean, it's on your formula, so you don't have to remember the number. You just have to remember that, oh yeah, it's accelerating due to gravity. I need to use that number. Okay? All right, study hard on the weekend there, guys.